Hello students, welcome to class 12 physics. In this video we are going to solve numericals of chapter 6 electromagnetic induction. Two concentric circular coils, one of small radius r1 and the other of large radius r2, such that r1 is very much small than r2, are placed coaxially with centers coinciding. Obtain the mutual inductance of the arrangement. So here there are two solenoids which is coaxial, that means the center of both the solenoid is same, having the same axis. The radius of the smaller solenoid is r1 and that of the greater is r2. We need to find the mutual inductance over here. As you can see, there is a symbol of dot over here and cross in the bottom side. This shows that the current direction is like this. It is coming out and then going inside. Consider two extremely long coaxial circular coils of equal length L, smaller one inside the bigger one. Let small and big coils be coil number 1 and coil number 2 respectively. Their common area of cross section is suppose A equals to pi r1 square. The cross sectional area over here, that is pi r1 square. Let I1 be the amount of current that is passing through the small coil. Let N1 be the turns of the smaller coil, and the magnetic flux linked with the big coil is phi2. So when the current is passing through the smaller solenoid, then flux associated with this second coil, that is denoted by phi2. So phi2 is equals to NB A cos theta. So here, because the flux is associated with the second coil, the number of turns will be N2, and here the flux is associated due to the magnetic field lines that is generated by coil 1. So taking that as B1, and A is the common cross section for both the coils. So taking in general A, and here theta is equals to 0 degree because the magnetic field and the cross section A, that is the area vector, both are in the same direction, both are parallel. So theta is 0 degree. So phi2 equals to N2 B1 A cos 0 degree. That is phi2 equals to N2 B1 A. Now here the magnetic field due to the coil 1, that is mu 0 Ni, because we are using a solenoid over here. So the magnetic field associated with that is mu 0 Ni, and that is due to the magnetic field of the smaller coil. It is mu 0 Ni1. Here N is nothing but number of turns per unit length. So we can write over here is mu 0 N1 by L I1. Thus phi2 equals to N2 mu 0 N1 I1 upon L into A. Taking I1 over here in the denominator, we get phi2 upon I1 equals to mu 0 N1 N2 A upon L. Here phi2 by I1 is nothing but M21, that is mutual inductance of second coil towards the first coil. Therefore M21 equals to mu 0 N1 N2 A upon L. Similarly, when I2 current is passing through the first coil, that is the big coil, which has N2 number of turns, then the magnetic flux associated with the small coil is phi1 equals to N1 B2 A cos 0 degree. So here we will be having N1 B2 A. Here it is B2 because the magnetic field lines associated with the smaller coil is due to the first coil, that is N1 mu 0 N2 I2 upon L into A. Here again taking I2 over here, on the opposite side we get phi1 upon I2 equals to mu 0 N1 N2 A upon L. Here phi1 upon I2 equals to M12, which is nothing but mutual inductance of first coil towards the second coil. So M12 equals to mu 0 N1 N2 A upon L. So from equation 1 and equation 2, we can say that M12 equals to M21, which is equals to mu 0 N1 N2 A upon L, where A is the cross-sectional area of the small coil, that is pi R1 square. So student, you may note down this numerical. Now numerical number 10. Obtain the expression for the magnetic energy stored in a solenoid in terms of magnetic field B, area A and length L of the solenoid. Consider a solenoid of cross-sectional area A, length L, volume V equals to AL and self-inductance L. Suppose current passing through it at time t is I and the rate of increase of current is di by dt. At this instant, if the magnitude of the self-induced EMF across the inductor is epsilon, then we have epsilon equals to L di by dt. Now, if the electrical power in the conductor is P, then P equals to epsilon I, because here we are knowing that general equation for the power is potential difference into the current. So, instead of the potential difference over here, we are using the induced EMF. So epsilon I, and we know the formula for the induced EMF, that is L di by dt. So P equals to L di by dt into I. Now taking dt on the left hand side, we get P dt equals to Li di, and we know that power is equals to work upon time. So P, taking T over here, equals to W, that is P dt equals to dW. So the time rate of work is power. Therefore, from that formula we can write power into the time as work done. So dW equals to Li di. Above is the work to be done against the self-induced EMF to increase the current by amount di. That means to increase the current, the work is to be done, whose formula is equal to Li di. This work done gets stored in the magnetic field inside the solenoid in the form of magnetostatic potential energy. So the work done is stored in the form of the potential energy dUB. Thus, replacing this work done with dUB, we get dUB equals to Li di. Now, to get the total potential energy, we need to integrate the terms on both the sides. That is, integration from 0 to UB, dUB equals to integration from 0 to I, Li di. So, over here, integration of dUB, we get it as UB, taking lower limit 0, upper limit UB, and on the right hand side, L will be common, it is constant, so it is taken outside. Taking integration of current, we get I square by 2, lower limit is 0, upper limit is I. So equating this, we get UB equals to half Li square. So the magnetic field inside the solenoid is B equals to mu 0 Ni, where N is nothing but number of turns per unit length. So B equals to mu 0 N upon L into I. So taking I as subject, in this equation we get I equals to BL upon mu 0 N. Also, the self-inductance of a solenoid is given by L equals to mu 0 N square upon L into A. So, using the equation of the current and the self-inductance in equation 1, that is for the potential energy, we get UB equals to half mu 0 N square A upon L into B square L square upon mu 0 square N square. So, here L gets cut, N square cut, mu 0, this gets cut. So, we are having half B square into AL upon mu 0. Here AL is nothing but V, that is the volume. So, the potential energy UB equals to half B square upon mu 0 into V. This expression of total magnetostatic potential energy is stored in the magnetic field inside a current carrying solenoid having volume. So students, you may copy down this numerical. How does this magnetic energy compare with the electrostatic energy stored in a capacitor? Magnetostatic potential energy stored in a solenoid per unit volume is called as the magnetostatic potential energy density. Her symbol is rho B. So the potential energy per unit volume gives the potential energy density. So for magnetic field it is rho B equals to UB upon V. And writing the equation of UB, we get rho B equals to B square upon 2 mu 0. And this equation is similar to that of the electrostatic potential energy density rho E. That is rho E equals to half epsilon 0 E square. So when you compare both this equation, we can see that in both this equation mu 0 is constant over here as well as epsilon 0 is constant. So the density is proportional to the square of the magnetic field in case of the magnetic potential energy, and for the electrostatic potential energy the density is proportional to the square of the electric field. So both equations are analogous. So students, you may copy down this numerical.